Hi, welcome to Pure Virtual C++ 2023. Today, we'll be going over MSVC's progress in implementing the C++23 standard. I'm Stefan T. Lavavej. I work on the Visual C++ Libraries team, and today's presentation will be about both the compiler and the libraries. So let's look at a recap of what has happened. The last Pure Virtual C++ was in April 2022, and right after that, the 17.2 update of VS 2022 was released, and we knew what was going to be in it. So we described everything that happened there. We had completed C++20's defect reports, and we had enabled the format and ranges headers in the stood C++20 mode. So in the year since then, we have released four production-ready updates, 17.3, 4, 5, and 6. When you're watching this, 17.6 is the current production release. And when a production release is available, we release almost always on the same day, although not every time, the preview of the next update. So 17.7 Preview 1 is the currently available preview version, and I'll be talking about that too. So those are highlighted since they are the current ones. And you're watching this in June 2023. Let us talk about the compiler. So C++23, like all C++s, is split into the core language and the standard library. Although many users don't really think about that distinction, the core language is what you get when you don't include or import anything, compiler features. So in the last year, we've implemented one CS+23 core feature, which is technically considered a defect report and thus implemented retroactively to C++20. That improves some things around the char8 t-type for UTF-8. We've also implemented a ton of compiler bug fixes and improvements, addressing many different standard features, but particularly header units and named modules. So I keep track of everything that I've reported as I work on the standard library, and I counted them. There's been at least 45 fixes for the standard library scenarios that I am aware of, and more things have been fixed probably that have improved the STL, and I just wasn't aware of them with a tracked bug number. So we get feedback from users through developer community and internal usage with teams throughout Microsoft. For example, Office has been very eagerly using header units to improve throughput. They've been reporting bugs and we've been fixing them, which then improves the experience for all users. So we expect to make more progress implementing the remaining CS+23 compiler features in the next calendar year, that's 2024. Right now, our priorities are helping customers adopt all the features that we've released in CS+17 and CS+20, especially modules. Modules is going to be a decade-long migration effort. And we're also working on improving the diagnostic messages. So when you get compiler warnings and especially errors, they can often be extremely inscrutable, and we're trying to improve that. So that's where we are with the compiler. For the standard library, we have released a ton of features. So here is the status chart that I always like to show. There's the URL in the top there. And this, as usual, is the count of remaining features in every standard since we began tracking this in about mid-2017. So a quick refresher on these lines. These count features just one for one. So one paper, one feature. We don't count patch papers when there is a paper that has been voted into the standard and then modified by other papers, and we haven't implemented any of them. We just all consolidate them and count them as one feature here because those extra patches don't represent net new work. But if we do implement a feature and then later something is voted in that modifies it, we count that as new work. So these numbers may not exactly correspond to other implementations, but they're a decent measure of how much work we have remaining. And when it hits 0, we believe we're done. Also, these are counted simply one for one, no scaling based on difficulty for implementers or utility to users. So the smallest feature and the largest feature, they're all just one, they count as one here. So with all that said, I've drawn a big line showing where we were as of the last Pure Virtual C++ conference. Every time this line goes up, that means that there is a standards meeting that has voted a bunch of papers in. So you can see the enormous spike mid-2022 for CS+23 features and a few smaller ones after that. And then when the line goes down, we have been merging features from our amazing contributors on GitHub, in addition to MSVC maintainers themselves. So currently we have 12 features remaining out of many, many that have been voted in. I forget the exact number. I probably should have added it up. It's something like 80 or more. Don't quote me on that as an exact number. You can see we track all of our progress in the open on the Microsoft STL repo. So you can see tracking issues for every single feature that we've implemented and merged and the ones that remain to be done. So let's go over every update that's been released since the last conference. And I'm going to list all of the STL features. This is taken from our change log on our wiki. I highly recommend reading that if you have not yet. And I'm highlighting all the ones that I'm going to be covering with examples later. So I'll be going very quickly over them here, and then we'll see more detailed examples later. So in 17.3, the first update after the last conference, we added the expected header. We implemented some deprecations for the aligned storage and aligned union types. Those were added all the way back in TR1 and C++ 11, but they are not useful really in a world with align of and align as. So they are now being deprecated in 23 and will hopefully be removed in the future, particularly because align as can handle what we think of as over-aligned types, whereas aligned storage and aligned union, they were implemented long ago enough that they don't handle over-aligned types, which is a significant limitation. We had constexpr unique putter, they're extending the reach of constexpr to every corner of the known universe, and a few ranges views. So ranges was a CS+20 feature, but CS+23 is dramatically extending it by adding new views, new algorithms, and chunk slide and chunk by are some of those new views. So 17.4 was a particularly large release for MSVC. This really just has to do with the timing of how long the release is open for changes, except in rare cases when we've got a big feature and an update is just about to go out and we would rather have more time for it to solidify. We generally don't really pay attention to what the next release is and try to, hold back features or anything. We just merge them as they get ready. And if a release happens to be open for changes for a long time, well, it's going to accumulate a lot of changes. And that's exactly what happened with 17.4. It also helps to know that traditionally, although I don't believe we absolutely guarantee this, the even-numbered MSVC updates, so 17.2, 17.4, and the current 17.6, these are considered long-term support by Visual Studio, meaning that we'll service them with patches for an extended period of time. So although, again, we don't guarantee anything, we do tend to keep these releases open for longer for changes from developers, and that means they just sort of naturally accumulate more stuff. So we have implemented all the features listed here. For completeness, I mentioned the library part of AutoXDK copying the language, but we have not yet implemented the compiler part of that feature. We've implemented stack trace. We're going to see that one with an example. That one's very cool. Not highlighted with an example, but a very large and very important feature is the P1206R7 conversions from ranges to containers. And my coworker Casey Carter worked on this. This encompasses both ranges 2 that allows you to take a range, possibly after it's already been filtered and transformed through various views, and then convert it back to an actual container object. So you could say, I want a vector out of this, whatever that final element type is. This also implemented new member functions for containers. As I recall, it's like assign range and insert range and things like that. So more integrating the ranges library with the classic STL containers, which is very useful. We've got a small constexpr feature for type info. We've got more ranges, view stride, that allows you to, as I recall, skip over elements of a range. We've added constexpr to careconf. That one was actually not too difficult because it was only the integral part, not the floating point part. Ranges algorithms to ask, do you contain this or do you contain a subrange? You can now have your own types, participate with range pipe. This is where you type the pipe character and you can send data through a sequence or through a series of ranges, I should say. More additional ranges cleanups. I could talk forever about these. Each of these lines, they seem like a really tiny feature, but a lot of work had to go into each of them from our contributors and from the maintainers and from everybody on the standards committee. So I'm devoting very little time to each one, but each of them can be quite useful. So this is continuing actually the list of features in 17.4. There were too many. I couldn't cram them all onto a single slide. More ranges algorithms. We've got substir, a method on string that now works on R values for increased efficiency. Forward like that can be used for generic code, although there are some very subtle gotchas there. Correctness improvement or safety improvement for string view. So if you're constructing a string view from a range that now needs to be explicit, I believe that can be a breaking change in some cases. If you've been upgrading your Visual Studio, you should have already encountered this breaking change several months ago. So moving on to Visual Studio 2022 17.5. Unlike the previous release, this one only had 3 C++23 library features, some ranges, algorithms, fold left, fold right, and a few others, basic format string and W format string, which help increase the utility of the format library, and then a tiny little paper, standard library module, std and std compat, that was, I think, 3 or so pages of standardies. I was a co-author on it. That was a large feature. So here's some fun statistics. I had to manually audit 148,000 lines of headers. The pull request, which you can view on GitHub, changed over 6,400 lines, and I had to manually add over 3,750 occurrences of export, because only through that manual process could we mark every publicly accessible identifier in the STL as exported for use by users through the modules. So that means we want to export something like std sort, but not something like std underscore capital sort underscore unchecked, because that name is ugly, as we call it. That's internal, and we don't want to expose it in the standard library modules. So we had no automated way of doing this, so we had to go through the human manual method and write test coverage and report and fix a bunch of compiler bugs, all that stuff. We're going to be seeing how that works, because that is a very important feature. Continuing on to the current production release, 17.6. This is another long-term release with a bunch of features. We've got more ranges algorithms. Find the last occurrence of something, or find the last occurrence if it satisfies a predicate or if it doesn't satisfy a predicate. Improvements to whether things are considered Boolean testable. Improvements to cbegin. More comparison, extending the reach of comparison concepts. One of the features I'll be demoing is actually an IO streams. You thought we were done with that back in C++ 98. Surprise. A new option has been added, IO space nowhere place, that can be useful. We've got another view allowing you to repeat an element. And we've got a feature that actually extends expected, which was added in CS+23. This is just something, a patch paper that was added after we initially merged the feature. I'll be talking about that, even though it doesn't have a top level example. Some slight improvements to the barrier specification and poison pills for argument dependent lookup in ranges, and a small tweak to views that helps improve their safety. So finally, the current preview release, which will be production at some point in the future, although we can't say when, has a fair number of CS+23 features in it. It's got an empty std float header. I guess I should talk about that because people are very curious. CS+23 is adding the notion of extended floating point types. These are optional. An implementation is not required to implement them. It is required to provide a header called std float. That is required to have an empty namespace std at least. That is what we provide. We don't provide anything else there. In the future, we might decide to add such extended floating point types, but currently we have no plans, if you're curious. We are, looking out for customer demand. So if there's sufficient demand for such types, we could put in the effort to implement and test and support that forever. But right now, that's not on the plan of record. So the big feature that we're adding here that I've got a example for coming is the print header. This is sort of a companion to the format header. What print does is it combines formatting something and then printing that to either the standard output or standard error streams, or any IO stream of your choosing. We've got more views. Views enumerate that, as I recall, allows you to apply something to every element of a view, or sorry, every element of a range, but also know what index it's at, which was added, I believe, at the last moment to CS+23, and we've implemented it. Significant improvements to tuple pair and tuple-like objects. This sort of generalizes support we informally had in functions like tuple count. Zip, which seems like a very tiny feature, it's just 3 letters, but it was actually a very large feature that had to be implemented in multiple stages by multiple contributors, which we're all very grateful towards. This has things like, I'm going to forget it because I didn't write the examples, but it's like a pairwise and adjacent. I'm probably forgetting it. That allows you to combine ranges and then process elements together. Other things that we've added, some restrictions. You can't specialize allocator traits. And there's a slight update to Unicode. So we are now going to stay in sync with every updated Unicode standard. If it changes what code points are considered emoji and things like that, we're currently synced to Unicode 15. And then another update to how iterators are specified. Very arcane, but important, and we've implemented that. Okay, so let's talk about some examples. So this first one, I'm actually not going to provide any code here, but I've got a link, so we'll talk about that. CS+ has the notion of vocabulary types, and these are extremely important because these are types that express such a common idea. Ordinarily, I would say concept, but I'm going to say idea here, that you want to be able to say in your code easily, and that you want different parts of a code base and different libraries, including third-party libraries, to be able to talk about. It's just nice when everybody shares a common vocabulary rather than, oh, I have to use a third-party header, and now I have to use its own notion of what a container is or what a range is. You know, libraries are always going to have to do specific, unique things, but as much as possible, if they can use common vocabulary and common algorithms, then it's easier to interface that with other code. So we've had since C++ 17 the optional type, which says I might have a T object, but I might not. And we've had the variant type, which says I am exactly one of the following types. I could be perhaps an int, a double, a string, some user-defined class. What is being added in CS+ 23 is something that's kind of similar to this, but not exactly. It's expected. You have expected, which takes a type and then an error type. And the expected object either has the expected type, the first argument, or it has the unexpected error argument, but it's never valueless. So it either has the value that you want or it explains why it's missing. In that respect, it differs from optional, because if you have an empty optional, it's not going to tell you why you didn't get such an object. Expected could store an error code. And it doesn't have to be a std error code. It could be an integer. It could be any user-defined object that you want, or a library-defined object. And unlike variant, expected is kind of like a variant because it stores one type or the other, but variant is a very generic and powerful interface because it can store any number of types at compile time. Expected just has two. It's got the good type and the bad type. So it's simpler to use, but it still avoids dynamic memory allocation like the others, all that. You can use it with exceptions. If you use the, I believe, value accessor, it will throw a bad expected access exception, but you can also use it without exceptions. And in fact, the new feature that I mentioned, the monadic functions for expected that patched this expected header, enables new patterns. It goes by the fancy functional programming term monadic, but really it just means chaining a series of function objects or callable objects to process what is stored in an expected and intelligently handling the cases where it has an object or it has the error condition or the error code. My coworker Cy Brand has written an extensive blog post about this feature. I've created a short link to it with the aka MS URL. So if you type that in, you'll be able to read that blog post and learn all about both expected and especially this monadic functions that was implemented later in 17.6, the current production release. Okay, so let's talk about stack trace, a large feature implemented in VS 2022 17.4. I have a fully worked example. It is too large to fit in this slide, so I have a link to Compiler Explorer here. That link contains only the code right now. It doesn't run it in MSVC or anything, but you'll be able to copy this and use it in MSVC. The critical thing here is when you compile this, you need to build with debug info. So that's the /ZI option here. Z7 would also work. That is what allows the stack trace to actually understand what frames it's looking at. So the idea here is that you can call a special static member function stack trace current. And this will give you an object, a stack trace, std stack trace, that represents the current call stack of the program from all the way in Windows where the program started through the CRT main startup to your program to the actual call of stack trace, to the thing that called stack trace current. So here it has some optional parameters. You can go look up how they work. Here I'm going to pass the integer 1 because what I'm doing is I've got some exception struct here. You don't have to use stack trace with exceptions, but this is a natural scenario. And it's going to be too many puppies, a runtime error. When I construct this thing, I don't want to record automatically where it was called from. But in this case, I know that I'm within the too many puppies constructor. That part is not interesting. So I'm going to pass the number 1, telling it to skip the topmost frame, which will always be the too many puppies constructor. And I just want to capture the thing that constructed the exception. Then later, if I can access this stored stack trace, I can iterate through it because it provides begin and end. So I can use a range-based for loop here or any algorithm if I like. Its elements are these objects called stack trace entries. And given an entry, I can ask, what's your description? And that will be an encoding of the function and the position within the function. We'll see how that looks. It kind of looks like the Visual Studio debugger. You can also ask the path to the source file that produced it and the source line. So I'm going to print out all those. So if I compile and run this, what we're going to see is at the bottom, because I'm printing this out in order, the highest part, the closest to the construction of the too many puppies exception is first at the top. And then the stuff in Windows that starts up the program, that's at the bottom. So reading from the bottom up, we can see something in NTDLL called something in kernel 32 to initialize a thread. Then we get some CRT startup machinery. This is in our statically linked portion of the VC startup library that's automatically linked by Visual Studio. Here you can actually see some of the source paths from our build lab. Our internal directories are called source VC tools CRT and so forth. And then finally, you can see the main function calling an outer function, calling the inner function in my meow.cpp program, and the line numbers there. And this was all captured automatically. So you do not need to call the Microsoft specific APIs to capture a stack trace and walk it and decode it in the PDB. We have done all that for you, thanks to our amazing contributors. I believe it was Alex Gutenyev who implemented this. And you can now call this portably. This will also work on other platforms. Of course, the actual output will be different. The output is highly implementation defined or unspecified. This is what we've chosen to do for now. Okay, so standard library modules. I talked about this. This has perhaps the simplest example, but the most following slides explaining how this stuff works. So you've probably heard about modules. Modules, the compiler feature, were added in C++ 20. And it came in the form of both header units, which is a transitional mechanism, we'll see about that, and named modules. Additionally, in C++ 20, the standard library is specified to work with header units. So several updates ago, we shipped standard library header units with full test coverage and increasing number of compiler fixes. So for a while, you've been able to import angle bracket vector semicolon as a header unit. What C++ 23 is doing is it's taking the existing core language support that was added in CS+ 20 for modules and saying in CS+ 23, there are now these new standard library modules named just stud and stud compat. We're going to see how they work. So if you're building Visual Studio, much of this will automatically be handled for you. But if you want to know how the actual command lines work, we are now shipping a special file, actually a pair of files, called stud.ixx and stud.compat.ixx. These are source files, and they are right next to the included directory. Here I'm using the VC tools installer environment variable that's on every Visual Studio command prompt that will correspond to your install location. Modules there is a sibling directory of the included directory that vector and bitset and algorithm and all those live in. So stud.ixx and stud.compat.ixx are just source files that we ship. You can see their implementations. You can also look them up on GitHub. You need to compile that with substantially the same compiler options as used as your program. So here I've got the command line. Then once that is built, and that's a one-time build, you only need to rebuild that if you change your compiler options or upgrade your Visual Studio toolset. It emits a .ifc file, which is a binary representation of the compiler's digested understanding of the entire standard library. In a special format that my coworker Gabriel Das Reis has been working very hard on. He's been spearheading this effort. And then once you've got that stud.ifc, it contains it's produced alongside a companion stud.obj. There's an actual object file that's produced. It's fairly substantial, and this is good. The compiler is able to emit implementations and actual code gen of various things like inline functions that it's encountered along the way so they can be reused later. The build of stud.ifc and stud.obj is typically very quick. I measured it at something like 3 seconds on a developer machine. It'll be faster or slower depending on how fast your machine is. And we're going to see exactly how big it is. Then when you consume it, you need to link against stud.obj. So I've shown that in the command line. Additionally, if the IFC file lives in a different directory, you need to pass additional compiler options to tell MSVC where to consume it. If it happens to be in the same directory, it'll implicitly find it, which is the hello world case here. And then to actually use this thing, all you do is you say import stud, semicolon, and you are done. You now have access to the entire C++ standard library, and you can use everything in namespace stud. So here I'm using both std_cout and std_printf. So as I mentioned, there are 2 named modules. So it's important to understand, and this is not really the place for a full tutorial on how modules work. We've got blog posts, and we'll hopefully have other content, including documentation. We've got some of that already that my coworker Tyler Whitney has worked extremely hard on. That's on Microsoft Learn. So the quick refresher is that modules are orthogonal to namespaces. They can go together, and indeed they do for the standard library modules, but they don't have to. So in this case, they actually do go together. When you import stud, you gain access to everything in the stud namespace. That includes all the C++ standard library stuff like stud vector, but also the things in the C wrapper headers like std_printf, std_fopen, things like that, std_int8t, for example. Now, the standard library modules are very special because they have extremely fine-grained control, and this is a good thing, over exactly what they export. So they export only the names in namespace stud. They do not leak names into the global namespace, at least according to the standard. We've got an implementation issue there right now. But you should pretend that they don't actually emit anything in the global namespace right now. However, many programs right now, they unintentionally or intentionally rely on the fact that for MSVC, if you include something like C standard IO, you get not only std_printf, but you always get the true name global namespace printf, :printf. So existing programs tend to be extremely fond of using C names, C standard library functions and types from the global namespace. You could go convert your program over to use stud qualification for all these things and then use import stud. Certainly for new programs, new code, we recommend doing that. That's why it's got the short, convenient name. But if you have a legacy program that is being migrated to standard library modules, we don't want to, and by we, I mean the standard, don't want to force you to have to go qualify all your stuff. So in that case, you can simply import stud.compat, which is a named module that goes and imports stud for you and gets you everything from that. So all the stuff in the stud namespace. And then it additionally provides all these names in the global namespace. So you will still have to do some other conversion stuff. We'll talk about that when you migrate your code, but at least you won't need to go qualify all your calls to printf and fopen and in32t and all that stuff. So that's named modules. It's helpful to understand where this fits in sort of the universe of consuming C++. So I like to think of several different ways, starting from the oldest to the newest. So classic includes, you say pound include, angle bracket vector, and however many C++ headers you need. All that does is, as we all know, it textually includes the source file content of that header that we have written in the standard library recursively or transitively. So a vector needs to include internal implementation headers, and if that includes utility, we're going to drag it all in. If you preprocess the entire STL as a 17.7 preview 2, that's about 7 megabytes of code. That is a lot of source code. And it needs to be recompiled for every translation unit, every single CPP that includes any of those headers. Now, we have, for many decades, shipped something called precompiled headers, or PCHs. If you look at how big a PCH is for the entire standard library, it is big. I just tested it, and it was 1/4 of a gigabyte, 254.8 megabytes, and that increases whenever we add stuff to the STL. For example, when we implemented the print header, it got bigger because we've got all this machinery. So why is it so big, and what is a precompiled header? People often have a very sort of hazy notion of what it is because none of the documentation really explains. Well, the secret is that a precompiled header is just a compiler memory snapshot. What the compiler does is it uses virtual alloc to reserve space at a specific virtual address in memory which is fairly easy now in x64 because there's just so much, virtual addresses. And then it very carefully puts all of its allocations in that virtual address range, including using STL allocators to control how containers like vector allocate memory. Then it takes all that, all those data structures, including with pointers interlinked in there, and it snapshots them to disk. And then later it reloads all that content, pointers and all, back into memory at the exact same virtual address, and then it goes from there. So it's literally a compiler memory snapshot. It's clever, it's quick, but it requires a ton of hacks basically in the compiler, and very large space on disk. And it's still not perfect because all that intermediate stuff that the compiler had to do, all those data structures, they all have to be loaded. It's not really digesting the standard library in any way. It's just sort of short-circuiting the compilation process and being able to reload it from an earlier point in time. Not the greatest. Header units are sort of an intermediate mechanism. We can, if we build all the header units for the STL and topologically sort them, which means when one STL header uses another, actually build that first, the smaller header first, and then import that as a header unit when building the header that depends on it. You need a lot of code, a lot of compiler options to do this. It takes a while, and it emits, something smaller than precompiled headers, but not perfect. Name modules. They boil the entire standard library down into a single IFC file and a single object, like I mentioned, and it is incredibly efficient and compact because the compiler has an optimized representation in this IFC format. Currently, and this will change over time and probably grow, the entire standard library occupies about 32 megs as an IFC with an additional about 2 megabyte object file. And then that can be used to very quickly import the entire standard library. So essentially what this does, and I'm not a compiler dev, so this is sort of my understanding summary. The IFC is sort of an index representation in a highly structured format of the entire standard library. So when you say import std, the compiler loads those indexes and tables, but it doesn't go load all the content that it refers to. It simply says, okay, I know how to find std vector, I know how to find std sort if the user uses it, but I can look that up on demand. That's why just import std is so incredibly fast. Name modules have the best compiler throughput possible, just incredibly blazing speed, and it's going to get better over time. And they have this ability of exporting only user visible machinery. Finally, the design of them, the fact that they were designed to be monolithic, meaning there's just a std module or just a std compat module if you choose that one, it means you no longer have to play the game of, wait, did I use an algorithm that's actually defined in numeric? Or wait, this is uninitialized copy. That's not actually defined in algorithm at all. That's defined in the memory header. Oops, I need to go include that. None of that stuff. You just import std, everything's available, and you don't need to worry about over importing. This also avoids the long-term maintenance burden of library restructuring, breaking your code because you were depending on the standard library dragging in something indirectly, and then a new version or migrating to a different platform entirely has broken that assumption. Import std is not ever going to do anything like that. So it is also important to understand the current progress of standard library modules, implementation-wise, and various design limitations. So modules is an incredibly big feature. I hear a lot from customers, why are there bugs? Why is it still not 100% done? And the answer is really that C++ is an incredibly complicated language, and modules have been added late in its lifespan. I mean, we've got 20, 30 years of legacy code out there and 20, 30 years of language complexity that has been added. This would not have been as difficult if modules, somehow if we had managed to specify 20 years ago, but that was not possible. We're only getting it now. So we need to represent every single wacky thing that you can write in C++, from bit fields to R values to concepts to all the stuff that ranges does and constexpr and constinit and all these things in a module with the full complexity of the code that something like the STL or Boost or user code can write. That finds a lot of bugs, and we're fixing them, but it is not an instant thing. So MSVC is continuing to work on fixing compiler bugs. 17.6, I can say from firsthand experience, has significantly improved quality. We reported a lot of bugs as we implemented the standard library modules that first shipped for production use in 17.5. And 17.6 was the release where the compiler has fixed a whole bunch of those bugs. Still not 100% perfect. We're still tracking and finding things, but it is getting much closer to a flawless experience. IntelliSense is a work in progress. You will see squiggles, you will see errors. You should expect this. Do not expect IntelliSense to perfectly handle standard library modules yet. In particular, at this point, we have not yet been able to enable automated test coverage for the STL with IntelliSense. We're really trying to get to that point soon. And when we do, we're going to lock in the current state of quality and then ratchet it upward, making sure we don't regress behavior. And also, you may have heard that we support both MSVC and Clang as first-class citizens for MSVC's STL. That remains true for standard library modules, but we need that compiler support to exist. Clang, I've seen on their status page and on the mailing list, they are working hard on implementing compiler support for CS+20 modules. When that becomes complete, then we will look at enabling test coverage in the STL and making any implementation changes as necessary to support Clang just as high quality as MSVC. But that's not the case right now, so don't expect that to work. We're also working on build system support. So in 17.6, we've got MS Build in the IDE automatically building the standard library modules. There's still some corner cases, like if you've got PCHs enabled, things like that, that may break, and we're looking into improving that. Separately, we know that many customers are very fond of using CMake, as we use ourselves when building the STL open source. We can tell you that CMake support is planned, but we don't have an ETA to share at this time from Kitware. But they are hard at work on it. So one major limitation you must be aware of when using modules with MSVC, because this is something that should work according to the standard, but it doesn't right now, is that if you import std, you should not at this time classically include any STL header. So do not import std and then #include angle bracket vector or the other order. If you attempt to do so, the standard says it should work. So please understand, like, this is not a limitation of the standard. It's our limitation in the compiler, that if you #include, which dumps out in the preprocessor stage all of the content of the vector header, and then imports std or vice versa, the compiler is unable to deduplicate this. It sees STL machinery coming from two radically different paths, and it basically is always going to fall over. You're going to get horrible compiler errors. Do not be surprised. So right now, and we know this is a major blocker for migration and experimenting with it, you have to convert translation units entirely over to import std. So there's one minor exception. I'll get to that. So the other thing, and this is a by design limitation in the standard, is that unlike classic includes and unlike header units, when you import a named module, it does not emit any macros. So the STL, the C++ standard library itself, does not emit very few standardized macros. There's only a few. There's like a couple like atomic init. Most of the time, though, almost never. It's the C standard library that, as we all know, relies fairly heavily on macros. That includes assert. It includes error no. There are things like offset of. These macros are not emitted by import std or even import std compat. So if you need those macros, you can include, according to the standard, and it should work in our implementation, the classic C headers, the ones that end with .h. The reason why this works is because the C headers are all wrapped in an extern C block. And that tells the compiler and it tells the module's machinery, this stuff doesn't belong to a module. It's just plain old C stuff. So it's not going to get confused. The STL itself extensively uses assert.h, so I can basically guarantee that that works. The other headers like errorno.h should work with import std, but if you encounter problems, please let us know. However, if you try to include the C wrapper headers, the C assert, the C errorno, those drag in STL internal headers, and you should not expect that to work alongside import std. This is something that I would hope future proposals for the C++26 timeframe and beyond address. I'm not aware of any work right now, but if somebody would like to step up and write such a proposal, some sort of companion header that emits only macros for the C standard library that can be included alongside import std could be useful, or potential other mechanisms. I don't know what they would look like. So a couple other caveats or design choices that seem mysterious when people hear about it. So as I mentioned, the standard library modules, we are shipping them as source files, std.ixx and std.compat.ixx. This is our choice. Other implementations may choose other things, but this is what we've chosen to do. We do not, and as long as I have a say in it, will never ship pre-built modules for these standard library modules. So you will not get a .ifc binary file. You will not get a .obj for any mix of compiler options. And this is 100% intentional. This does demand that you actually have your build system build it. Build that IFC and build that .obj, which takes, like I said, 3 to 5 seconds and like 30-something megabytes of space. But what this means is that that built module that you build yourself on your dev box or your build lab will fully respect all of the compiler options you've chosen, all of the library modes you've chosen, and all the warning suppressions. Everything that could possibly influence the content of the standard library, the modules will respect that. So this is important. Right now, we only have C++ 23, which is the mode that standard library modules work in. But there's going to be a C++ 26. There's going to be a C++ 29 and beyond. You will be able to select any of those standard modes going forward with your standard library modules. You will be able to set your library to release or debug. You can turn on warnings, turn off warnings. If you want to live dangerously, you can change our iterator debug level, things like that. You can restore removal. So if we've removed autoputter, you can, which we did, you can restore that. That is our one exception to very strictly exporting only standard things from the standard library modules. When I went and implemented this, I said, okay, for the identifiers and machinery that we have removed over time, and provided escape hatches for, if you activate that escape hatch, the standard library module will respect it. Even though technically it never existed at the same time as autoputter, yeah, we'll export it for you. So final point of confusion, very common confusion that I want to mention, is you may have heard, if you've been following MSVC's progress, we had these things called experimental modules, and you will still see documentation about them. You'll still see options in the installer and the IDE. So these standard library modules std and std_compat are completely distinct from the old experimental modules std_core, and there are some others. The plain std and std.compat, those are the standard ones. The experimental ones, we are still supporting them for our users who were very eager early adopters. We love such users. We don't want to break them unnecessarily. So they're still being supported, but they are not encouraged right now because they were always intended to be a stepping stone toward the standard library modules that are actually in the CS+23 standard. We have achieved that wondrous goal. So now is the time to start migrating to the actual standard ones. With the standard library modules, std and std_compat, you do not need to select any optional components in the VS installer. We always install that std.ixx and std.compat.ixx source files right next to our headers. And you do not need any special option, which was called experimental module. You don't need that for import std. All you need is std C++ latest, or std C++ 23 once that option becomes official. Right now, it doesn't exist. Very common point of confusion. We're looking at what can we document? Should we perhaps, do something about the old experimental modules? Right now, we haven't done anything, but just be aware that they are 100% distinct. So let's move onward. That was a big feature. 17.6. Let's talk about a small feature. So this is iOS-based no replace. So again, a link to Compiler Explorer where a fully worked example lives. Here, if you pass the new option iOS-based no replace when constructing a file stream for output, so either an OF stream or an F stream that actually wants to create a file, if the file does not already exist, then constructing that OF stream will make it. It will create that file on disk, and then you can stream whatever you like to it. Here I print cats. I know, surprising for me. Then if you go close that file, if you try to construct an OF stream with the iOS-based no replace option, and that file already exists, then the OF stream will not attempt to override it. It will not attempt to open it for appending or truncation, none of that. It's just going to say, I'm going to enter a fail state. You asked me not to replace the file, and yet it already exists. So I'm going to say it's an error. So here we can see that if I prepare my file system by cleaning out anything that already existed, if I call test once, it can successfully create the file. In this case, it was named something like no replace example.txt. Then if I close it, and if I try to construct an OF stream with no replace again, it fails the second time around, saying output file already exists. This is known as exclusive mode in POSIX and C, but as the actual paper mentioned, no replace is kind of a more intuitive name. So this is now added. The amazing thing is we were able to do this with still supporting binary compatibility. So thanks again to our amazing contributors for finding out how to do this. I probably would not have expected that was possible. So finally, the last example that I have for you is the one that is currently in preview. This is the print header. This was a very large feature, and it is cool to see. It looks very small, especially in this example, but a ton of things are happening behind the scenes, and it enables something that is both very simple and very cool. So you can use it without any special compiler options, but the experience will be best if you tell the compiler to use UTF-8 for string literals. So if you pass /UTF-8, that will tell it, please understand that all my string literals will be in UTF-8. Honestly, this should be the default. Right now, it's not. This also not only makes print work better, it also increases efficiency with format, the std format header. So when possible, please try to use this compiler option. So here I've showed two of the functions that the print header provides. If you call printline, you just give it a string, and it will print that followed by a new line. So you do not need to say \n. This is sort of the print version of puts, put string from the C standard IO library. The different thing about println is that puts, the classic puts, would simply take a string literal or const star and just print that out unmodified, not interpret any format specifiers in it. Whereas println will totally respect any format specifiers, so you can have, as the following line shows, braces and then give it extra arguments. So the next line shows how that works. If you call the std print function, this does not append a new line. So if you want one, you need to explicitly put it there, as I've highlighted. And you can use the format header style specifiers, either just empty braces to say, hey, just print this argument and you know what the type is, or you can say, I want it in hexadecimal format. That's what the :X means. And then finally, I've got an example where I give println a Unicode escape. So if I use the core language syntax of \U and then 8 hexadecimal digits, the Unicode character 1F63B, I wonder what it's going to be. Well, we're going to see on the next slide. Surprise. If we actually compile and run this thing, the first line prints hello world followed by new line. The second line substitutes in formats that number 1729 as hexadecimal and substitutes in the string kittens. And then finally, that Unicode escape is printed to the console as an emoji, and it gets all the way through the Windows console and does not get mangled. This seems simple, but it is actually incredibly impressive. It required a lot of work from our contributors to make this work based on all the legacy behavior of the Windows console and the CRT, and I could go on forever about how it works, but it works, which is great. So that is how std_print works. It should not only be a very powerful feature, but it should also be a very convenient feature, because now you can just print things without having to use IO streams. You don't need to say that left shift operator that's so confusing to newcomers, and also is harmful to localization because you were mixing code and data. With print, you don't need to do that anymore. You can have a format string, and you don't need to intersperse it with those shift operators. So that was a lot of examples. As with the last conference, we'd like to give you a little explanation of what's next. So as I mentioned, especially in calendar year 2024, we're going to start focusing on implementing C++23 compiler features. There aren't that many, actually, but there are a few, and there are some library features that depend on compiler support. So we're going to be focusing on that, things like consexpr for CMath, and I actually forget all of the compiler features that remain to be implemented. We're also going to merge and continue reviewing the remaining C++23 STL features. There are 7 that don't need compiler support from our GitHub contributors. These are, let's see if I can name them from memory. They are the generator proposal from coroutines that my coworker Casey Carter is working on. We've got flat map and flat set, which are going to be very useful container adapters. We've got the formatting ranges feature, and we've got a couple small features like formatting thread ID and stack trace that will enhance the format feature. And then, although they don't exist right now, there's going to be committee meetings that are going to add STL features to C++26. So as before, We will almost certainly hold off on accepting and reviewing pull requests for C++ 26 until we are actually done with C++ 23's STL. But when we are, and hopefully that will happen soon, no promises, but hopefully soon, we'll start opening the doors to implementing C++ 26. Probably that will happen once we have a compiler option, but that separates 23 from 26. We'll have to work out the logistics of that. So, as before, this is not just an us thing, this also requires your involvement. If you are an eager user of C++ 23 and modern C++ standards in general, and you are, otherwise, why would you be watching this very arcane presentation? You can help drive the C++ ecosystem forward. So wherever you work, or maybe you're a hobbyist, whatever you contribute to, try to help upgrade your production code bases to the latest version of VS 2022 with all the latest features and the latest supported compiler option for production, which is std C++ 20. You can also experiment with std C++ latest, which would be great. Like try out import std, but technically we don't support that for production, and we can break binary compatibility for the latest option until it is fully final and we add the std C++ 23 switch. That's the main caveat there. But if you want to, scout out your code base with that option, please, that would be amazing. You can also install Visual Studio previews. As I always like to say, they work side by side with the production version. It's not going to contaminate your machine or anything, and so you can try out the latest features, the latest compiler fixes. If you do encounter any compiler IDE bugs, please go to the Visual Studio developer community and file an issue there. Those will be seen by the compiler and IDE team, and they can be appropriately triaged, and they can respond to you, ask follow-up questions. If you find any STL bugs, you can report them to developer community, but we prefer that you report them directly to our open source repo, github.com/Microsoft/STL. And we'll be able to work directly with you on investigating it and telling you when we've merged a fix and all that. So that has been the MSVC C++ 23 update. Thanks for watching and enjoy the rest of Pure Virtual C++ 2023.